Okay, welcome to the third lecture in the first part where we are trying to design a crank rocker mechanism. Now we'll go over the first approach for designing this, then we will look at the second approach. Each of it approaches have their own advantages and disadvantages, as we will see. Now, in this, design is always about choice. So we have to make some choices, and then the others get determined once we make a few choices. So we are going to start off with selecting the position of the fixed pivot of the rocker. So we'll do that. So we say, okay, the rocker fixed pivot has to be situated. So in our wiper case, it's like saying, okay, here is where the fixed revolute joint has to be located. So we do that. I'm calling that O4. Then I'm also going to make a choice, say, of link length 50. All right. So 50 rocker, I know it is where the fixed pivot is going to be. The floating pivot, therefore, is going to be on a circle, because the rocker is going to rock back and forth as part of a circle, centered at O4 with a radius of 50 millimeters. So here is a sketch of that, what I've drawn. So I have arbitrarily picked, say, B1 here, and then from there, if you draw a 70-degree angle, and then I can get B1 prime here. So I can have several choices. I could have picked, for example, so I could now go back. Let me open up OneNote here. Let me just a second. If you give me a second, I'll open OneNote here. Let me add a page. So we have chosen basically a so O4, which is out here. And now you basically have a choice of a circle which is going to be centered at this, my bad circle, doesn't matter. Now I'm going to essentially pick various positions. So one possibility is to say that I have something like this. Let me choose a blue color. And so 70 degrees from here, so I have another, so this is my B1, and this will be my, say, B1, B-1A, I'll call it. So this is one choice. I could have another choice which is like this, and therefore it will come somewhere here. So this is B1B, and I could have a B1 prime B, and so on. So now remember, because it's a Grashof mechanism, my choices will have to be either in the upper part or in the lower part. I could operate in the lower part of the circle, so I could make choices like this, or I could happen. I cannot make a choice where B1C, for example, let us now let's pick a color. Let's see, what color should I choose? Let me choose add pen. Let me choose a red one. So I cannot choose. This is not allowed. So I cannot choose. Say this is my B1C, and therefore let's say that is 70 degrees. That is B-1C. So this is not allowed. So this is not possible because of Grashof cannot cross. This is crossing line of pivots. Of course, I don't know that as of yet, but okay, maybe I'm jumping the gun a little bit. We don't know where the pivot is. Assuming that it is along this line, then it cannot cross the line of pivots. Okay, we will leave it like that. We'll come back to this anyway. So you can see that there's a wide variety of choice. I can pick B1A at some orientation as one extreme position, then I can go to another extreme position. All right. So we'll come back. We'll revisit that anyway. All right. So we have a choice. The choice that I have made, of course, is to choose this position B1 to be out here. So this is the choice that I have made, and then corresponding B1 prime, because we are using a 70-degree angle between the extremes. That is what it is. So these two extreme positions get dictated. Now, I have chosen alpha to be 40.8. Now, don't tell me why is this arbitrary 40.8. Remember the animation that I showed you. I constructed the animation and then found out that alpha was 40.8. I kind of did it backwards. Just sat down and did this on GeoGebra, and lo and behold, I got a design. So it turned out that alpha for that case is 40.8 or about 41 degrees. Okay. Now, in general, you could draw an arbitrary line. In now, how do I bring this alpha into the picture as far as the design is concerned, right? So we draw an arbitrary line from B1. So this is the choice we made, right? From B1. So I will draw an arbitrary line, and so essentially I'm going to do that. Let's go back, and what I will do again. Let me show you what we mean by that. Let me go back, add another page. So here, let's go back. I have my fixed pivot here, O4. I have made a choice. Let me use a blue line so that is my B1, and 70 degrees away from that is my B1 prime, right? So what we are basically saying is, look, this angle that you make at the other fixed pivot, I can now determine that. So this angle, so first I draw an arbitrary line. So I draw this line. So this is B1D. So this is drawn arbitrarily. I could choose to draw this, for example, I could draw this is B1D1. I could draw another line which is B1D2. I could draw a third line which is, sorry, it is moving. A third line, close. I could draw a third line which is like this. So I could draw various lines. But the upshot of this is that now I need to draw a line which will basically go, let me use a green color here, which will basically from here to B1 prime. So this angle has to be alpha. So similarly from here, if I draw a line, that angle has to be alpha. So you see that there are a number of choices where the fixed pivot, the other fixed pivot essentially comes into the picture. So, so for this rack or choice, so here is the crank pivot location. So this is, I showed you. So I've drawn an arbitrary B1D. So here is a B1D line that we have drawn. And then this line is basically drawn at that 40.761 to be very precise. 40.8 is 40.761. So this angle is alpha. So the intersection basically, if you recall the extreme positions, the intersection happens to be the point O2. So here is my O2, which is located here, and therefore now the design is basically very easy to do. So from B1, so we drew an arbitrary line B1D, and then from B1 prime we drew a line B1 prime E, which makes an angle alpha at to the B1D line. So this intersection gave us that. Now if I go back and look at this O2 B1, so this locates my O2. O2 B1 is, if you look at this, longer, so that represents L2 plus L3, and O2 B1 prime represents L3 minus L2, because remember the crank is the smallest of these links. So therefore, now I have the design complete. So the coupler length is simply 1/2 of O2B1 plus O2B1 prime, and the crank length is of course 1/2 of O2B1 minus O2B1 prime. Lo and behold, so we have a design now. So essentially I have located O2, and I also have the crank lengths that I have chosen, right? So it so happens that I have chosen L4 to be 50 mm, and it happens that L1 is about 40 mm. And for the rocker positions that we chose, B1 and B1 dash, if you go through the calculations, you get that to be 14.3 mm crank and 72.7 mm coupler. Of course, we double check to see that this is a crank rocker design. The largest link is 72.7, which is L, and the smallest is 14.3, which is S. The other two, P and Q, are 50 and 40. If you add that, it turns out to be L plus S is less than P plus Q. And since S is the smallest link and the link next to it is basically fixed, you get a Grashof mechanism, and of course you can show that it is a crank rocker. Now the same animation I'll play out for you once again. This is what we designed earlier. Of course, I'm just showing you that once again. So this is built for a 70-degree extreme positions between the two rocker extreme, the angle between the two rocker extremes. So you can see that animated here. Okay, so that's 70 degrees. Take it from me that it is 70 degrees. So we have done that. Now, What are the choices that we have for O2? So we remember we drew BD, B1D arbitrarily, and then we drew a line from B1 prime at an angle of alpha to the B1D line. Now, obviously, there are many such lines that can be drawn. So let's go back and look at the same picture here. So remember that this angle that we are talking about, which is between this angle, is essentially alpha, right? The angle that is subtended by B1 O2 B1 prime is always alpha, irrespective of what the orientation of that B1D line is. So I could have drawn a different line of orientation B1D2, and then I would have got a E2 such that the angle made at O2 is always going to be alpha. So what does this mean? So this has a consequence. So if you vary the orientation of B1D, the point O2 is now going to move on a circle. Why? Because the angle doesn't change. Alpha is independent of, is a fixed quantity in the design. And irrespective of what the orientation of B1D is, I'm always going to get an angle alpha, which means for different B1D, O2 is going to move on a circle. And it so happens that B1 prime is the chord of that circle. So this is a very important concept that you have to look at the geometry, that when you look at this B1 dash and O2, O2 is moving on a circle. So here is the locus of the circle. B1 prime happens to be the chord of this circle. Now, of course, since I know 3 points on a circle, B1 is on the circle, B1 prime is on the circle, O2 is on the circle, and O2 is the one that is moving because I'm fixing B1 and B1 prime, and I'm changing the B1D line orientation, therefore O2 keeps changing. So O2 is basically moving on the magenta circle. The center of the circle is at C that I have marked there. So you can see that I have marked the circle. So therefore, I have a number of choices, and it's interesting that the choice, the O2, as I keep varying the orientation of the B1D line, I get O2 to move on a circle, which is shown here. So therefore, I get a number of design choices. All right. Now, it turns out that there are certain positions which are not allowed for O2. So you can see I have reproduced that O2 line. I have removed the B1 prime line corresponding to O4 for clarity. You can see that I have marked two regions which are in gray. So here is one part of it, so B1 to B1 dash, and similarly here between P and R, which if you notice is nothing but if I have extended that B1 O4 line to intersect this circle at P, and similarly B1 prime O4 line, if I intersect to R, O2 cannot lie there. Now, why can O2 not lie there? Remember, this is a Grashof mechanism, and if O2 were to be chosen in one of these gray points, then B1 and B1 prime are on opposite sides of the line joining the fixed pivots. Now, for a Grashof mechanism, the rocker cannot cross the line of fixed pivots. You could start with a design where it stays below the fixed pivot line or it stays above the fixed pivot line, but you cannot have one position of the rocker which is below the fixed pivot line and one position which is extreme position which is above the fixed line. So it has to remain completely above all the positions of the rocker will have to be completely above the line joining the fixed pivots or completely below. Either of these is possible. So therefore, that comes from the fact that the rocker cannot cross the line of fixed pivots. Those grayed out areas are basically the ones where we cannot choose. Otherwise, so you see a number of choices exist. So there's a fairly large zone here where I can choose O2. Similarly, over here that I can choose O2. So I have from P to B1 prime, and similarly from here to here. So many choices that are possible for O2. And this is for a given alpha and theta, which is 70 degrees, right? So you can see that the everyone can come up with a different crank rocker design, right? What I showed you is one crank rocker design, but each of you can come up with your own crank rocker design. Good. So now, what if we want? So this is turns out that this particular case is for TR greater than 1. So and now what if we want TR less than 1? So this is a case where alpha is negative. Now how do we find the crank positions for these? So what we do is we basically reflect this center C that we saw, which is the center of that circle on which O2 is moving. We reflect that about by drawing the perpendicular bisector of B1 B1 dash, and the center H basically of a circle, and here is what we will see. This is the circle that we are seeing. So I've taken this point C and reflected it about B1 B1 dash. So you draw a perpendicular bisector, and this distance is the same as that distance. And then when you draw a circle, obviously it passes through B1 and B1 prime. Now, using the same logic, remember that the line, the Grashof thing basically dictates that one cannot have the rocker crossing the line of fixed pivots. So the gray area is a lot larger for the negative one. So you can see from T to V along this, and again from B1 to B1 dash over here. So there's a small zone T to B1 prime and B1 to V, which is drawn in magenta. I can locate an O2. So there's a small zone in which we can choose. Still, we have some choices that we can make. This is for a negative alpha. All right. So those are the allowable pivot positions. I have done such a design. I will show you an animation of this. I leave you to figure out that this is indeed one where the return is slower than the forward motion. So here is the forward motion in the return. You can see the return is quite slow. I'll play again. Convince yourself that indeed the return is slow. So it's still, so here is the forward motion. And now the return. Okay. So anyway, I think you will have to convince yourself that that's indeed the case. Okay. All right. Now, what about the TR equal to 1 design? In this case, remember that alpha should be 0. So that means the angle between the two extremes should be 0. So we have a very nice simple situation that the pivot should be basically on the line joining B1 B1 prime. So since the angle alpha has to be 0, so your choice has to be along this line. So I have arbitrarily picked O2 out here. So along the B1 B1 line extended, obviously the dashed portion is one which is not allowed, because if I choose O2 to be lying on that, again we violate the Grashof mechanism condition that the rocker cannot cross the line of the fixed pivots, line joining the fixed pivots. So again, I have done a design. The parameters are here. We can make a sanity check to make sure that it is indeed Grashof. The numbers are given here. Okay, and just as a check, I have plotted the two extreme positions for the rocker. It turns out that, of course, now please, not to confuse you, but my crank is now on this side. Earlier, the crank was on the left side. Now it is on the right side. So this has become my crank here. Earlier, I was drawing it here, but this time around, I have reversed it. So this angle is about 25 degrees, where these are in a line, and again at 205 degrees they are again collapsed into a line. So you can see 180 degrees for the forward, and therefore 205 back to 25 is another 180 degrees. So this would imply, so this is a quick check for me that the time ratio that I have designed is indeed equal to 1. Alright, so here's an animation of that, what I have designed. So I mean, again on the right side is the crank. So unlike the earlier animations where the left part of it was the crank, so the green one is the crank. So you can see that we are going through. This is a 1:1. I'll play again just for your. Okay, now the return stroke. Fine, good. So you can see that essentially now we have been able to do the crank rocker design. So the approach basically, let me summarize before we close this video. The way we have carried out the design is we said, okay, well, let's fix up choose the location of O4, which is the rocker fixed pivot. Then we chose a certain length for the rocker, and we came up with a design where we found that O2 will be located on a circle, which is basically the procedure I have told you how to construct on the circle. There were certain positions for O2 which were not allowed because of violation of the crash off condition, that the fact that it is a crash off mechanism. And then I also showed you how to do this for negative alpha as well as TR equal to 1. TR equal to 1 is a simple case because essentially the choice is to be on the B1 prime line outside of course, points in between B1 and B1 prime, right? Okay, so we will now come back and look at the second approach. And the reason for that disadvantage of this approach we will examine when we look at the second approach, and then we'll go through that design and formalize that design. One could use either of these, but as I said, you will have to know the pros and cons of this approach that I have talked about so far in this video vis-a-vis the second approach, which I'm going to talk about in the next couple of videos. Okay, so see that. If you have any questions, please feel free to post it on the forum, and then I'll try to answer this. Okay.